this is example 10-6, where we have flow from a pressurized tank. So we have this tank here, and there's a pressure inside of the air that's on above the water. And so the water is going to flow from the tank through the pipe and out at B. Now this pipe, of course, will have major losses just because it's a pipe, galvanized iron, but we'll also have losses at the two elbows that we have here, 90-degree elbows. We have a gate valve up here, and of course we're going to have water flowing into this pipe through an entrance. So we'll have all those different losses. Now we are supposed to find what the flow is. So for that, we need to start out with the energy equation. So let's start here with the energy equation. Energy equation. Not a whole lot of space here. So we're going from A to B, so we'll have PA over gamma plus VA squared over 2G plus ZA plus H pump, and then plus, not plus, equal to PB over gamma plus VB squared over 2G plus ZB plus H turbine plus HL. Cool. We already know that our losses are going to be both minor and major losses. Now let's go through and find all the different terms. So we can start out with a datum. Where do we set the datum? I will say that we set it at A, right? Set our datum right here at the surface of that of the water. So datum at A, that means that ZA, of course, is equal to 0. And ZB, let's see. So we go 6 meters up, but we already have the 1.5 meters here, so that'd be 4.5 meters. 4.5 meters. All right, so that's our datum. We know that point B is in contact with the atmosphere. Point B in contact with atmosphere. That means PB equal to 0. PA we're given, right? That's up here, 300 kilopascals. So we have the P's. That means we need the velocities. Okay, VA, of course, A is going to be somewhere here. So we can say point A at surface of reservoir. Means that VA is equal to 0. Now VB, I guess we don't know what VB is. No, we don't know what VB is, right? Because we don't know what the flow is, so we can't say what VB is, so we'll just leave it as VB. But what else do we know? We know no turbine and no pump. So no turbine or pump means that H pump equal to H turbine equal to 0. And then, so we don't know what VB is, but we know that it's constant along the entire pipe. So maybe just write that down. So constant diameter means that VB, we'll just call V, is the same everywhere. Except, of course, inside of the reservoir, but that's fine. We don't have any losses there. So that means we have, let's see, we've talked about the pressures, velocities, the elevations, and the shaft work. So all we're left is HL. HL will have two components. We'll have the major loss along pipe. I guess we could just say major loss because that's always the one along the pipe. So that's going to be HL, let's say MA for major, and that is F times L over D times V squared over 2G. Now, normally, right, we'd figure out what the Reynolds number is, and then with the roughness that we're given, when we give it a galvanized iron pipe, so we could figure out what the roughness is, we would then go into the Moody diagram and figure out what the factor is. However, we don't know what the velocity is, so we can't get the Reynolds number. So we can't really say much more about the major losses right now than what we have right here. So then let's look at the minor losses. Minor loss, and what do we have? We have two 90-degree elbows. Two elbows. Right, that would be our elbow here and here. We have the gate valve up there. Gate valve. And what else? Well, we have the entrance right here, where we have water flowing like that. And entrance. So we can say our HLMI for minor, right, is then just all the different factors added together. So we have a KL from the gate valve. We have 2 times the KL for an elbow, and we have the KL for an entrance, and all that times V squared over 2G. Again, we don't know what V is, but we can go and look up what all these factors are. Right, so for a fully open gate valve, we know it's 0.19, it's pretty low. Then we have the 2 elbows, right? Say these are smaller diameters and not like sweeping ones, so that would be 0.9. And then for the entrance, for the flush entrance, we have 0.5. V squared over 2G. Add all those values together, we get 2.49 times V squared over 2G. All right, so with that, we have all the preliminaries done, and we can go in and write our energy equation again, right? So we said we know the pressure at A, so PA over gamma. We said the velocity was 0, we said the elevation was 0, and we said that the H pump is 0. Then we looked at point B, the pressure is 0 because it's at the atmosphere. Now we do have the velocity term here, although we don't know what V is yet. We have an elevation, don't have a turbine, but we have HL major and HL minor. All right, so let's write these all together. Leave out all the zeros, so we have PA over gamma is then equal to V squared over 2G plus ZB. Now plus, where's our, up here's our major one, right? That's the form that we already know. Let's pull that F up there. F times L over D times V squared over 2G. And then we can just barely see the minor one. That was 2.49 times V squared over 2G. All right, so we have a whole bunch of terms that depend on V, and so what we're going to do is we're going to write an expression for V, for the only unknown in there is F, and then we're going to assume an F, and then we can calculate what the V is, which means we can calculate what the Reynolds number is. We can look up what our friction factor is in the Moody diagram, and then we can keep on iterating until we kind of get to a stable solution. But to do that, we first have to solve all this for V. So let's get all the non-V terms on one side. So that would be PA over gamma minus ZB. And then we can pull out the V squared over 2G. So that leaves us with 1 plus F times L over D plus 2.49. So that we can pull those two together. So let's see what we want to do with this. Well, let's pull those together maybe. Do that first, right? That's PA over gamma minus ZB. You know what? Let's already multiply this by 2G. Get that over here. Is equal to V squared over 3.49 plus F times L over D. Right, we got that together, which means we can now divide that all and then straight up take the square root. So we can say V is equal to the square root of 2G times PA over gamma minus ZB divided by our term right here, 3.49 plus F times L over D. All right, so now we have a term for V that only depends on F, right? Which means we can now go ahead and we can assume an F and then calculate what our V is. Now, I don't think it's kind of a long expression here, so maybe we'll just see if we can write this down here. I have enough space. So we can say V is equal to, we can write that here, I guess. We can say assume F is equal to 0, 0, 3. Now, there's really no rhyme or reason to choose this number. I like to choose it because it's kind of somewhat in the middle. You can choose something else if you want to. But let's start with 0.03. So what does that mean for our thing here? So we have 2 times G, which means 2 times 9.81 meters per second squared, times the pressure. Let's see what we had. We had 300 kilopascals. So times 300 times 10 to the 3 Pascal. And that was, scroll up just a little bit so we can see our equation, divided by gamma. So we don't have gamma, so we'll do rho times G, so 9.81 meters per second squared, times, what is our rho? It's not given to us, but the water's at 20 degrees, so we can look that up. Turns out that is 998.3. So 998.3 kilograms per cubic meters. That's that term. And then we need to divide this by 3.49 plus F, that's the one that we just assumed, 0.003. The length, let's see how long our pipe is. So we have 4 meters here, plus 6 meters there is 10 meters, it's 12 meters long. Right? That's how long my flow is. Times 12 meters divided by the diameter. Probably should have looked it up last time I was up there. Diameter is 50 millimeters, so 0.05 meters. 0.05 meters. And of course we can plug that into a calculator. And that gives me 6.92558 meters per second. Right? Again, this assumes that the friction factor is 0.03, which we don't know if that's true or not. Right? So what we're going to do now is we're going to figure out what the Reynolds number is. RE is rho times V times D over mu. We already looked up what the density is, 998.3 kilograms per cubic meters. Velocity we just calculated, 6 times 6.92558 meters per second. The diameter was 0.05 meters. And that all divided by mu, which we'd have to look up. And for 20 degrees, that's 1.00 times 10 to the minus 3 Newton seconds meters squared. All right, so if we plug that in, we get 3.46 times 10 to the 5. Right, that would be our Reynolds number. So we're clearly in turbulent flow. So we'll have to use our Moody diagram. To do that, we need to look up what our roughness factor is, what our roughness is. Doesn't say it specifically, but it says galvanized iron. So we can go look that up. Galvanized iron pipe, I guess, put there. We know that epsilon is 0.045 millimeters, relatively smooth. All right, so we then can say epsilon over D, right? That's what we need for the Moody diagram, would be, I might have looked that up wrong. It doesn't look right. That is the wrong number. Right, that's why it looked so that this would be steel, right? Galvanized iron is 0.15 millimeters. Let's double check on our table here. Galvanized iron, yeah, I had the steel written down for some reason. No. So that's 0.15 millimeters divided by the diameter, which was 50 millimeters. Oh, not zero, it's not meters because we have the top in millimeters. So it'd be 50 millimeters. That gives us a value of 0.003. So now with our Reynolds number and our roughness, we can go into our table and into our figure and read off what our F is. I already put the lines in, right? So we said it was 3.46, so it's just below 3.5 right here, and we said that we had 0.03. Now there's not 0.03 isn't there, but it's just halfway in between here, more or less. So we can just kind of look at where the halfway point is. Let's say this is the halfway point, and so we can read off. This would be 0.0252625, I guess, is probably where we're ending at. All right, so maybe we can do a little dash here. That'd be 0.0265 is what we'll read off. All right, so with that, we can do the same again, right? So now we assumed that it was 0.03. Based on our first iteration, we now say it's 0.0265. So it's pretty close, but it's not close enough. So let's do one more iteration. So we can say from Moody diagram, we get F is equal to 0.0265, which means we go back to our velocity and recalculate our velocity, right? Because we have a different F now. So we can say V is equal to the square root of 2 times 981 meters per second squared times our pressure, 300 times 10 to the 3 Pascal, divided by G times rho, meters per second squared, times 998.3 kilograms per cubic meters, minus 4.5 meters, now divided by 3.49 plus our new F, which was 0.0265. Length was 12 meters, and the diameter is 0.05 meters. And when we calculate that, we get our new velocity of 7.214845 meters per second. So let's see, what do we have before? Before we had 6.9, now we have 7.2, so not that far apart, but let's see what we get. So if we do our Reynolds number again, right, that's now 998.3 kilograms per cubic meters times our new velocity, 7214845 meters per second times 0.05 meters divided by 100 times 10 to the minus 3 Newton seconds per meter squared gives us 3.60 times 10 to the 5. What do we have before? We had 346, right? So, remembering what our graph looks like here, it's going to be a little difficult to make much of a distinction there, right? So we'll move our line just a little bit. We go back up here. We're already estimating where we are half in between, so these are getting more and more estimatey. So this is now, if we read this off, we can say that's maybe 0.026 instead of 265. And with that, we do our whole game again, just like we did before. Calculate our V and see where we got. So from Moody diagram, F is equal to 0.0260, and again the velocity. Now, at this point, I hope it's obvious that this is obviously something that you would want to do in a spreadsheet, right? Because then you can just pluck new numbers in here and not have to recalculate everything, because there's only the one number is changing, right? Only F is changing, so good idea to do this in a spreadsheet. 10 to the 3 pascals divided by 981 meters per second squared times 9983 kilograms per meter cubed minus 4.5 meters divided by 3.49 plus now our new F, 0.260 times 12 meters divided by our diameter, 0.5 meters. And that gives me a velocity of 7.2591999 meters per second. How does that compare to what we had before? 7.214. This is getting pretty close, right? So let's look at our Reynolds number to see if there's much of a change. Shouldn't be, because the velocities are very close. 9,983 kilograms per cubic meters times our new velocity, 7.2591999 meters per second times our diameter. And that divided by the viscosity, 1.00 times 10 to the minus 3 Newton seconds per meter. And with that, we get 3.62 times 10 to the 5. Now that is 3.60, so there's not much sense of redoing this again. All right, so we found our value. Let's say close enough. Right, because just moving the line just a little bit is not going to change the friction factor in any appreciable way, which is not going to change the velocity. All right, so now we have the velocity. If we want to get the flow, right, we just do V times A, which is, of course, V times pi over 4 times d squared, which is 7.2591999 meters per second times pi over 4. Not going to have enough space here. Times d, 0.05 meters squared. Squish it in there. And that gives me a flow rate of 1.42534 times 10 to the minus 2 cubic meters per second, or if you round this, 1.42 times 10 to the minus 2 cubic meters per second. All right, so that's the flow rate that we would get. Let's scroll all the way back on top here. All right, this is the flow rate that we get at coming out of B if we have this tank with pressure on it. Again, we first wrote the energy equation. Based on that energy equation, we noticed that we don't know the velocity, and we can't find what the friction losses are without the velocity, so we had to assume a friction factor and then do a couple iterations with the Moody diagram to finally find what our velocity is, and from that velocity we can then get the flow rate.